Thank you so much for the invitation. Uh, so I'll be talking about a little bit about two particular models where we've used quantum chemical methods to make more accurate computational predictions, particularly of complicated properties. And I always like to start out with the group, because of course the amount of work that I'm doing on this is small relative to what people are doing. And in particular, I'd like to highlight Omria Barbanel and Brianna Greenstein here, who have done the work and the projects I'm particularly going to talk about today. Okay, so our group, we're interested in using computational methods to drive materials discovery, particularly organic materials. And here's a graphic we came up with for a table of contents graphic understanding organic solar cells, polymer solar cells, right? How can we kind of borrow from computational drug discovery to help drive materials discovery? And of course, the problem is that a lot of the properties you might want to study involve a complex mix of multiple calculations. But the promise in this field is that there's an enormous number of possible molecules, an enormous number of possible polymers. And so, we can find the needles in the haystack, and hopefully there's more than just one. But I'm going to not talk quite as much about the discovery part in this talk. I'm going to talk about more how we can use machine learning and quantum chemistry together in order to predict the properties. Now, one thing that comes up is in computational chemistry, there's often a trade-off between speed and accuracy. This is a graphic we designed for a benchmark of conformer energies. And you can see on the one hand, the traditional force fields are quite fast. On the other hand, accurate ab initio methods like coupled cluster are very slow, on the order of days. This is a logarithmic x-axis. And the y-axis here is the correlation with those coupled cluster energies, right? So DFT methods are relatively accurate, but still on the order of hours. And then right here in the middle, actually, reflecting kind of a nice balance are these GFN methods from the Grima group and a couple of emerging machine learning methods as well. So the reason I'm mentioning this speed and accuracy trade-off is because the hope, the holy grail, so to speak, is that machine learning methods can push towards the accuracy of advanced DFT methods or ab initio methods, but with force field speed, we're just not there yet. Okay, so I mentioned interest in organic solar cells. I'm going to start with a little discussion about that. We started on this project because, in a solar cell, particularly an organic solar cell, you need two materials, one that preferentially conducts positive charges, one that preferentially conducts negative charges. And we know the solar spectrum, and so we can work out thermodynamically two key parameters, right? We need to optimize the optical absorption, the band gap, and we need to align the energy levels between both materials, because if I transfer an electron from one to another, I want that difference in energy to be relatively small, otherwise I'm losing a lot of voltage in my solar cell. And so this paper goes back to 2006. There's been a variety of models since then. They all have similar properties, saying, oh, okay, we want the band gap to be around 1.6 electron volts and so on. The catch, of course, is it doesn't tell us which molecule to make. It's an inverse design problem, right? We know the key parameters we want, but we don't know the molecules that give us those properties. But it's a very simplistic model. And so starting a few years ago, we said, look, maybe we can use machine learning and data from experimental devices, because what really matters is we have in current organic solar cells, we have two different materials. So we worry about the optical absorption of both of them. And it's not just a question of the band gap, right? You want to make sure that you also have a strong oscillator strength, so that you're absorbing a lot of the photons at that energy. And then you care about the energy level of alignment of both materials, as I said. And there's other things that may matter, right? The dielectric constant of the two materials affects the electrostatic attraction between the two charges. So there's a whole lot of properties that are relevant for predicting device power conversion efficiency. And in order to predict them using computational methods, you need to get accurate conformer energies and geometries, right? You need to predict the structure of the relevant species. And so we said, okay, well, let's build up machine learning models using quantum chemical inputs, right? We can calculate using DFT and TD-DFT, and then little bits of Python to describe things like the planarity of the molecule and so on, to put in the relevant properties, the dipole moment, the polarizability, the energy levels, the excitation energies, and the oscillator strengths, etc. And it works out quite well. The limit is actually the accuracy of the experimental data, which is sort of plus or minus 2% in terms of power conversion efficiency, and the limit of the amount of experimental data you can feed into it. So we've been building this up. Here's an example. This is actually version 2 of our OPEP, Organic Photovoltaic Efficiency Predictor. And you can see that the predicted power conversion efficiency is accurate to about 1.6%. On the test set, and it's about 1.4, so 1.5, 1.6%, and that's, as I said, largely limited by the experimental data. Now the great thing is, once you have such a model, then you can use it in generative machine learning, or in our case, we often use genetic algorithms to evolve new champion materials. And you can evolve not just one type of material, but you can use it to evolve in the final case, in that particular paper. We evolved 4 materials simultaneously to optimize the optical absorption spectra, optimizing essentially the number of photons absorbed, and minimizing the overlap of the peaks. And we think this is a great way to design 2-layer tandem devices with high efficiency. But, here we're feeding directly in a lot of quantum chemical data in terms of a complex property. But again, as I said, we're kind of limited by the amount of experimental data. More recently, we've been working on a different kind of model that we think shows a way that we can get around the amount of limited experimental data. So that centers around predicting molecular pKa, which is, of course, an important property for understanding the degradation of molecules, environmental stability, drug discovery, right? What is it, the relevant protonation state in the body? And work on this has generally centered around two types of models, right? So one is a purely quantum mechanical model. So using quantum mechanical methods of different types to predict the entire thermodynamic cycle of protonation or deprotonation and the solution. And then there's a variety of models that have used straight machine learning. Okay, we're going to put together a neural network, and then we're going to train on a bunch of experimental data, and hopefully we'll have an accurate model. But I want to mention here the range, the errors, the uncertainties, right? And they've gotten better over time, but generally the root mean squared errors are, sort of around 1 pKa unit. which is surprisingly not great, considering how important the model is. And so our goal was, hey, maybe we can use some of these quantum mechanical properties, for example, from GFN2, combined with a machine learning model. And so the machine learning model will essentially calibrate for the solution effects, microsolvation, etc. And we particularly wanted to center on what's called micro pKa predictions. So in micro pKa, you want to predict not just the overall pKa of the model, but what the pKa of particular sites might be, right? So for example, the deprotonation of this acidic proton or the protonation of a basic amine, right? This particular species can undergo both, and you'd want to know the pKa, for example, of the amine is around 2.7, and the pKa of the carboxylic acid is around 4.7. So that's the goal, right? We want to put together some machine learning method that takes the molecular graph, the molecular species, and then predicts the pKa of any acidic or basic sites on the model. Right, and then our goal is we want to integrate some of these quantum chemical features from GFN2. So that requires a whole workflow. You get the input molecule, but you have to do a search for relevant tautomers because the protonation of your input may not actually be the relevant protonation or tautomer state in solution. Then we need to figure out which sites are actually reactive. For example, those aromatic CH bonds are probably not reactive. And then we do the micro pKa prediction on each of them. So first, the tautomer search. How do we do this? Well, we use RDKit, which is a cheminformatics toolkit. We enumerate the possible tautomers. So for any given species, we may have, I don't know, a dozen or more possible tautomers that we've enumerated. We then do a geometry optimization in a solvation model so that we have essentially the optimized geometry and structure for that species. And then we take the one with the lowest energy tautomer and we use that as considerations of the most stable species. The next step, we have to do a reaction site enumeration. So here we borrow a tool, CREST, which allows you to do protonation and deprotonation search. The one catch with CREST is that because it's exhaustive, it produces a lot of possibilities. It takes quite some time. And so we built up 2 surrogate graph neural network models to predict the protonation or the deprotonation results from CREST. So we fed in about 1.5 million molecules from Kemble. We did CREST protonation searches and CREST deprotonation searches, and then we used those as training sets for the protonation and deprotonation site models. What do the models look like? Well, as I said, the key component of this is that we're treating the molecule as a graph, which is a natural way of thinking about molecules, sort of the valence bond approach. We put in a variety of features that are relevant from cheminformatics. Of course, the element, the atomic mass, van der Waals radius, is an aromatic carbon, for example. Number of hydrogen bond acceptors and donors based on cheminformatics rules. But we also put in quantum mechanical features, so the computed partial charge, the computed atomic polarizability, a Fukui index. We put in Weiberg bond orders, which are actually very helpful in terms of thinking about the protonation or deprotonation, because quantum mechanically you can get information about the electron density through those pairs of atoms, and oh, this isn't just a double bond, it's actually a relatively weak double bond. It's more like 1.8, or it's a single bond that's about 0.7, etc. And then we also feed in, most importantly, the protonation and deprotonation energies using the GFN2 model as well. Okay, so we're putting in both cheminformatics features and quantum mechanical features as well. Now, I don't have a tremendous amount of time. I'll mention the preprint of this paper is out. The model is available, and the paper should be accepted actually quite soon. We're just submitted the response to reviewers today. So the micro pKa model, the big problem is that there's not enough experimental data to really train a good neural network model. There's maybe around 6,000 data points, high quality experimental data points. And so how do we train a good graph neural net when we have so little experimental data? And the solution we hit up on was transfer learning. So again, as I said, we grabbed the 1.5 million molecules from Chembl. We basically dumped every data point from Chembl that had an associated predicted pKa. And that worked out to be 2.6 million predicted pKa, because of course many of these species have multiple pKa's predicted. So that's 2.6 million predicted pKa data points. And those were predicted using the ChemAxon, the commercial tool. So we fed those in, we trained up an initial model. Now the initial model is, again, not as accurate as we'd like. We then do transfer learning, retrain that model using the 6,000 experimental pKa models. The fine-tuned model is much more accurate than the original one. Importantly, our overall model includes two paths, right? So the first path is for the protonated states. So, we use the protonation site model and say, oh, look, we think this amine might be protonated. We're going to feed that into one path. And then the deprotonated site search, we deprotonate the carboxylic acid and we feed that into the other. And so the model actually includes both pathways in the overall micro pKa prediction model. How does it come out? Well, there's a number of relevant test sets. I'm going to talk about two in particular. One comes from Novartis. Another one is scraped from the academic literature. And these are used in a variety of evaluations of pKa models. And here you can see that the RMSC, mean squared error, on the Novartis set is below 0.8. And on the literature test set, it's actually closer to about 0.5. We've also compared ourselves on a variety of blind evaluations, the sample sets 6, 7, and 8. And there's a new one out, the Euro sample, that the submissions are due today. And we'll find out in a couple months how we did on that as well. So our accuracy and performance is excellent. We're beating all current models, including several which are commercially available. EPIC, for example, is from Schrodinger, and as I mentioned, the ChemAxon, which is what we were trained on. So you can see that despite training on the ChemAxon tool, our model is substantially more accurate than the ChemAxon, than the original data that we trained on. So I think I was supposed to keep this to about 20 minutes, so I'll have some time for questions. We like to use quantum chemical descriptors often from GFN2 because it's a nice balance between speed and accuracy, many other times with DFT in machine learning models. This has given us two models. One is state-of-the-art prediction of organic solar cell performance, and then we've also achieved state-of-the-art for pKa prediction. And I mentioned and went through the model for pKa prediction because I think it shows that doing pre-training on computed data is really helpful to allow you to work when you have modest amounts of experimental data. All our models are free, open source, and open data. You can get them on our GitHub page. And with that, I'd be happy to take any questions.